Let's solve the third of three problems that we have in this series, in which we are going to find entropy values in tables. Using steam table data, determine the indicated property data for a process in which there is no change in specific entropy between state 1 and state 2. In each case, locate states on a sketch of the TS diagram. And then we're giving problem A and problem B. Each has two states, state 1 and state 2. And we're asked to find the final temperature and another property. Let's look at the first problem. We have water. State 1 is at 40 degrees C, and it has a quality of 1, which is to say it's a saturated vapor. State 2 has a pressure of 300 kilopascals, which is 3 bar. And we're told that S2 is equal to S1. So this is a constant entropy problem. And in this first problem, we want to find the final temperature in degrees C. We want to find the change in internal energy for the water. Let's get values for state 1. We'll go to the saturation table for water at 40 degrees C. And we know that S1 is S sub G because it was given as a saturated vapor. And so we get a value for entropy for state 1. And we know that U1 is U sub G because, again, it's a saturated vapor. And we'll get a value out of the table for U1. Now for state 2, our two independent properties that define the state are that pressure is 3 bar and that the value of S2 is the same value as state 1. So we know that S2 is 8.5270 kilojoules per kilogram K. Now we won't find that value of entropy at 3 bar in the saturation table, but we find it in the superheat table. But we don't actually find the actual value. We find that it is somewhere in between these two rows. So at 440 degrees C, we have a table value of internal energy and entropy. And then at 500 degrees C, we have the same, and S is somewhere in between. So we're going to have to interpolate, and since we're looking for the final temperature and for delta U, we'll interpolate both the first and the second column here. Now I'm not going to go into great detail about doing the actual interpolations. If you have questions about that, go back to chapter 3 problems, where we solved interpolation problems in great detail. But I always like to get an interpolation factor. And that's a value between 0 and 1 that shows me how far I am between these rows. So if the factor was a half, our temperature and internal energy would be exactly halfway between the values in these two rows. But for this problem, using the knowledge of entropy, I can calculate the interpolation factor as 0.6025. And then I can interpolate final temperature for 76.15 degrees C. And I can also calculate the internal energy at state 2. So we're asked to find the change in internal energy during the process. Well, delta U is just U2 minus U1. And we now have table values for both of these. And we calculate that delta U is 660.39 kilojoules per kilogram. And finally, I'm going to draw a temperature entropy diagram. State 2 exists at 40 degrees C as a saturated vapor. So it's right here on the saturated vapor line. State 2 is directly above that because the entropy does not change. And state 2 also lies on this 300 kilopascal pressure line. So this is where we would locate state 2. Now the second problem is also water, and we're asked to find the final temperature and the change in enthalpy. State 1 is a temperature of 8 degrees C, and a quality is given, so we know it's a saturated mixture. State 2 has a pressure of 1 megapascal, which is 10 bar. And again, the entropy does not change during this process. So let's get values for state 1. We're going to go to the water saturation table at 8 degrees centigrade. And it's notable that the saturation pressure there is 0.0107 bar. So we're going to grab values for H sub F, H sub G, S sub F, and S sub G. And knowing the quality, we can calculate the state 1 values of enthalpy and specific entropy. So H1 is just H sub F plus the quality times H sub G minus H sub F. We'll plug in all our values. Calculate that the state 1 enthalpy is 2019.6 kilojoules per kilogram. We'll do exactly the same thing for S1. It's just S sub F plus the quality times S sub G minus S sub F. We have all those table values. And we get the entropy at state 1 is 7.1843 kilojoules per kilogram K. Well, now we need to get some values for water at state 2. And state 2 is defined by 2 independent properties. One is that its pressure is 10 bar. And the other is that its specific entropy is the same as its state 1. So we have a value for that now, 7.1843 kilojoules per kilogram K. We're not going to find this state in the saturation table, but we do find it in the superheat table. But we don't find a table value with this exact specific entropy. Instead, we find that this value falls somewhere between a temperature of 280 degrees C and 320 degrees C. So again, we're going to have to interpolate values for T and H based on our knowledge of the entropy and these 2 entropy table values. And again, I'm not going to go through all the interpolating details, but I do calculate an interpolation factor of 0.9205. And that gives me a final temperature of 316.82 degrees C. It also gives me a value for the state 2 enthalpy, which is 3087.09 kilojoules per kilogram. So now I can calculate delta H, which is what we were asked to find, and that's just H2 minus H1. Have both of those values from the table, either an interpolated value or a given value. And I calculate that delta H is 1067.49 kilojoules per kilogram. And finally, let's draw a temperature entropy diagram of this problem. State 1 is a saturated mixture with a quality of 80% at 8 degrees centigrade. So I'm going to plot state 1 right about here. We know that state 2 has the same entropy as state 1, so it's going to go straight up. And where this vertical line crosses our 10 bar pressure line, that's where state 2 exists. And from our table, when we were looking at state 2 values, we found that state 2 is a superheated vapor.